Welcome, everyone. My name is Xavier Bresson. I work in the Department of Computer Science at the National University of Singapore. I would like to thank the chairs of KDD, Feida Zhu, Ben Ching Oi, Chunyan Miao, and the organizers of the Applied Data Science talks, Alon Haliva, Ying Li, Vanessa Evers, for the invitation. So today I'm going to talk about the traveling salesman problem and how to solve it using the transformer network. This is a joint work with Thomas Laurent from LMU. So this is the outline of my talk. I will give a brief history of TSP. I will present the traditional solvers for TSP and then the recent solvers based on neural networks. I will show you the proposed architecture, the decoding technique, and some numerical results. I will give a discussion, and finally, I will conclude. So let me start with TSP. So you know TSP, so you have a list of cities, and the problem is to start at one city and then visit all other cities exactly once, and then come back to the original city with the minimum length. So this problem was first formulated by William Hamilton in the 19th century. And this TSP, this problem actually belongs to a larger class of routing problems that are used every day in industry, like warehouse organization, transportation, supply chain, hardware design, manufacturing, and so on. So TSP is a hard problem because exhaustive search is factorial time. But it is also the most popular and the most studied combinatorial problems, starting from 51 with the mathematician von Neumann. And TSP has driven the discovery of several important optimization techniques like Lagrangian relaxation and simulated annealing. So there are two classes of traditional solvers. The first class is exact algorithms where you get an exact solution. And the second class is approximate algorithms where you're going to trade exactness with speed. These algorithms, they are usually designed by iteratively applying a simple main engineering rule, which is called an heuristic. So let me review quickly these traditional solvers. So for the exact algorithms, we have dynamic programming with exponential complexity. Then we have Jurobi, which is a general purpose integer programming solver. And then we have Concord, which is a specialized version of Jurobi for TSP. So Concord today is seen, as the fastest exact TSP solver in existence. So you can cast TSP as an integer linear programming problem as follows. And I'm going to give you some interpretation of this equation. So the first term, which is the linear term, is the length of the tour. The second term, which is a constraint, is basically means that each city is going to be connected with two other cities. And the last term is if you take a subset of the cities, like this one and the complementary, then the tour is going, so this subset are going to cut the tour by at least 2 edges. If they don't cut the tour by at least 2 edges, it means that the tour is disconnected and it is not a feasible solution. So integer linear programming problems are NP-hard because the space of optimization is binary. It's a non-convex set. It can only take, 2 values, 0 and 1. So what you do when you are in this situation is that you are going to relax to the closest convex set, which is the interval 0, 1. And then you get something popular, which is the linear programming problem, which can be generally formulated as follows. So you're going to have a set of solution, which is called a polytope. And then you are going to have, the linear objective, and the x that you are going to decide is the one that is going to coincide, with the polytope. So solving this problem can actually be done in quadratic complexity. The issue is that we don't know the S. So we don't know when we are going to violate the feasibility of the tour. So each time, so we are going to identify this S iteratively. And this makes the problem untractable. It's just impossible to track all the S. And it's also called, cutting planes techniques. So each time you identify a S, you can add this constraint into the constraints. So what you do is that you add a new plane, so a new cut of the plane. So that's why you call that a cutting plane techniques. Another issue with linear programming is that you get a continuous solution between 0 and 1. So for example, for this edge, you may get, the solution 0.51, and then you need to make a decision. Are you going to keep this edge in the solution or not? So this leads to a tree of possible solutions, and the branch and bound technique is a way to discard some part of the trees where you can prove that there is no solution. Overall, the complexity of Concord and Jurobi is polynomial times the complexity Bn, which is the number of branches. So we don't know theoretically what is the Bn. So what we can do is that we can experimentally try to find out. So here you have in the x-axis the number of cities, and the y-axis is the time you need for Concord to solve the instance. The dark curve is Concord, and the blue curve is the approximation with the polynomial complexity, and the red curve is the approximation with the exponential complexity. So you see that for small number of cities, Concord behaves like a polynomial time algorithm, and then for a large number of cities, then Concord has an exponential time complexity. So for the approximate algorithms, the first one was Christophite's algorithm. Then there are insertion algorithms like this illustration, where you are going to insert, the farthest node to the partial tour, and so on until you get to a tour. Then you have the Google OR tools, which solves TSP and also a larger set of vehicle routing problems. And this use a set of heuristics. Another class of approximate algorithms is k-opt algorithms. So for these algorithms, you are going to replace two edges to reduce the tour length. Okay. So you can do it with two edges. You can also do it with three edges. This we call a tree-opt move. LKH tree is basically doing these moves, but you need to select the candidates, and the way they select the candidate is by using a minimum spanning tree. And this is the best heuristic algorithms for solving TSP today. So you can make a hierarchy of traditional TSP algorithms with complexity and exactness. Exactness means that this is the gap between the optimal solution and the approximate solution. So 0 means you have no gap, you get the exact solution. So of course, for exhaustive search, dynamic programming, and Concord, the complexity is high and you would get optimal solution, but for these algorithms, complexity is better, but you get an approximate solution. So let's look at deep learning for TSP, for the TSP problem. So deep learning has significantly improved computer vision, natural language processing, and speech recognition in the last decade by replacing human-crafted features by features learned from data. So for combinatorial problems, the main question is whether deep learning can learn better heuristic from data, so replacing human engineering heuristics. And this is very appealing because if you need to design a new algorithms to solve, to approximately solve NPR problems, this will take a lot of time for mathematicians and computer scientists. For example, TSP has been actively studied for 70 years. And there are many problems in industry which are combinatorial by nature. So the last 5 years, I've seen the emergence of promising techniques where neural networks and graph neural networks have been able, to learn new algorithms to solve TSP. So let me review these new algorithms. So first, Hopfield nets. So this is the historical neural network to solve TSP, and it was in '85. And more recently, there was the pointer net technique introduced by Oriol Vinals and his collaborators. And this is really the pioneering paper using modern deep learning to tackle TSP and other combinatorial problems. So what they did in the paper is, so they took the 2D cities and they make a representation of the cities using a recurrent neural network. And then they decode by also using a recurrent neural network to embed the decoding cities and an attention mechanism to decide which city is the next in the tour. So in this paper by Sami Benjo and his collaborators, they improve pointer net. So in pointer net, the network was trained by supervised learning. So they needed some approximate TSP solution to learn the network. So here they use reinforcement learning, so they don't need any more training data. In this paper, they improve again the pointer net. So when you use a recurrent neural network to embed the input city, there is a natural order. But for TSP, the order is meaningful. Is actually not relevant. So you need the network to learn to be independent of the order of the input city. So that's why this paper introduced order invariant encoder of the cities. In this work by Nazari and his collaborators, they use a graph neural network to learn a state value function Q to estimate the next city in the tour. So they train by reinforcement learning and memory replay. In this work by Johan Brunin and his collaborators, they cast TSP as a quadratic assignment problem, which is NPR, and they use graph neural network and supervised learning to train the network. In this paper, they solve a variant of TSP with a multiple Salesman. They train by supervised learning, and the solution they get is fractional, so it is a continuous solution. And they change this continuous solution into an integer solution by beam search. In this paper by Louis-Martin Rousseau and his collaborators, they use the transformer, the self-attention layer to encode the input cities. And then they decode recursively city after city by using a query composed of the last 3 cities in the partial tour. In this paper by Max Welling and his collaborators, they also use a transformer for the encoding of the input cities, and they decode recursively by using a query composed of the first city and the last city, and also the global representation of all cities. In this paper, we used a deep graph neural networks to train to predict the probability that an H belongs to the TSP solution. And then we decode a tour by beam search. In this work by Wu and his collaborators, so they try to learn a policy to decide which edges are going to move in this two-opt setting. In this paper, by Xing and Tu, they use a graph neural network with Monte Carlo tree search. And the idea was basically to look ahead. So when you make a decision, you cannot go back. So here the idea is, let's try to look ahead before making a decision. In this paper by Fu and his collaborators, they combine supervised learning and reinforcement learning. The supervised learning is actually our technique, which train a network to give a probability that an edge belongs to the TSP solution. And then they have a second step that use this edge probability map with reinforcement learning and Monte Carlo research to decode a feasible tool. They were able to get to a very large number of cities of 10,000. Recently, and there was also the paper by Max Welling that combined, again, supervised learning with our techniques to train a network to give a probability that this edge belongs to the TSP solution. And then they decode using dynamic programming with specific TSP constraints. And they get the best supervised learning solution for 100. Okay, now let's introduce our proposed solution. So what we will do is that we will cast the TSP problem as a translation problem, where the source language is going to be a set of 2D points, and the target language is going to be a tool with minimal length. The motivation is quite natural. So in the recent years, transformers has been a powerful architecture, and we wanted to apply this architecture to combinatorial problems. So we trained by reinforcement learning with the same setting as the paper by Max Welling for comparison. So here is the proposed architecture. It is composed of an encoder and a decoder, and I'm going to detail this architecture in the next slides. So here is the encoder. What we will do is that we will use self-attention layers to represent the input cities. So here is a kind of an illustration. So we will start, with 2D representation of the cities, and then the encoder will try to, get the best possible representation where the decoding of the TSP solution will be easy to do. So the decoder is going to be autoregressive, so one city at a time. So suppose that we have decoding the first T cities in the tour, and we want now to predict the next city. So to do that, we're going to have 4 steps that I'm going to detail now. So the first step is to give an input to the decoder. So the input, so let's say, for example, that we have decoding, this partial tour, and we are at the time T here. So the input of the decoder will basically be the encoding representation of the selected city at the previous time, IT. Okay. And then we will add to this vector a positional encoding, because we want to remember the order of the sequence. So the positional encoding is the standard transformer positional features. Part 2, so once we have the input of the decoder, what we're going to do now, we are going to create a query for the next city. So to create the query, we are going to use a self-attention layer between the input of the decoder and all cities in the partial tours that have been visited so far. Okay, so we use a self-attention layer to do that. Part 3, so now that we have the query, we can ask which city is going to be the next one. So we can, we can query the unvisited cities. So we use for that a cross-attention layer between the query and the unvisited cities. And finally, the last step, instead of using multi-head attention, we are going to use a single head attention. because we are only interested to the next city. So we need a probability distribution over our next city. For this, we are using a single head attention layer. Once we have the distribution, the possible distribution over the next cities, we are going to sample this distribution. So we can use Bernoulli during training, and then during inference, we can use, for example, greedy. So let's compare transformer for NLP and transformer for TSP. So the order of the input sequence is very important for NLP. The order of the words in the sequence is a strong information. But this is not the case for TSP. The order of the city is not relevant. So we don't have any positional encoding for TSP. But of course, the order of the output sequence is very important. This is the solution that we are looking for. For the self-attention layer, for the encoder, we are not using layer normalization like in NLP transformer. We're using batch normalization. And it works better because we have a batch of TSP of the same size. But for the decoding, because it is autoregressive, we are using a layer normalization. For training, we don't need any training data like NLP. We can basically learn by reinforcement learning by using the length of the tour as the reward signal. And both transformer for NLP and TSP have quadratic complexity. So this is the number of CT square times the number of layers. So now let's compare with the most related architecture, which are the work of Max Welling and Louis-Martin Rousseau. So we use the same transformer encoder with batch normalization, but our decoding architecture is different. So our query uses all cities in the partial tour. For Max Welling, they used the city, the first city in the partial tour, and the last city. And for Rousseau, they are using the last 3 cities in the partial tour. We also start differently the decoding process. We have a special token Z, which is a fake city. And this will talk with all the other cities to find the best, starting location of the decoding process. In the case of Welling, they are using a random token for the first and the current city, and Rousseau is using they are using a random token for the last 3 cities. The decoding technique now. So a tour is naturally represented by an order sequence of indices. And what we do is that we cast TSP as a sequence optimization problem. So we have this probability that we want to maximize that the sequence belongs to the TSP solution. So in the case of autoregressive decoding, so one city after one city after one city, we can factorize the probability. So the probability of having a tour is actually the product of the probability of selecting the first city times the probability of selecting the second city given the first city, and so on. So the decoding problem is actually a maximization problem of the product of the conditional probabilities. And these conditional probabilities are actually learned by a neural network. So once we have the conditional probability, now we need to decode. We need to decode a tour. So of course, exact search, we will get back to factorial. If we do greedy search, we will get a linear complexity, which is the best one that we can do. And here we just select the next city which maximizes the probability. And we can improve that by better sampling techniques with beam search or Monte Carlo tree search. But we will increase the complexity with the number of beams. Okay, I'm gonna skip that because of the lack of time, and I'm going to show you the results. So this column this column is the class, presents the class of techniques. So you have MIP, which is mixed integer programming with Concord and GRB. You have heuristic algorithms with like insertions, OR tools, and LKH tree. You have here learning techniques with supervised learning plus reinforcement learning and reinforcement learning. So here you have training data, and here you don't have any training data. This is TSP for 50 cities. This is TSP for 100 cities. This is the length of the tool. This is the gap. So this is, the optimality gap between the approximate solution and the optimal one. This is the training time, and this is the inference time. So Concord is our baseline, and so that's why the gap is 0%. But GRB is also, providing the best solution. The same also for LKH3. For learning techniques, the recent technique by Cool also provide the optimal solution. The same also for supervised learning and reinforcement learning, the technique of Fu. And if you don't use any training data, you see that our techniques provide the best solution, which is also close to the optimal gap. Here are some visual results. The red curves are for neural networks, and the blue are for Concord, with here the lengths. Here, this is zero-shot learning. So you train on the size of 50 nodes, and then you zero-shot on the size of 100. And you see that you are able to get an optimality gap also quite good, like 1.4%. So, of course, if you compare numerically the complexity between a Concord in black and transformer in blue, this is complexity and logarithmic complexity. Transformer is, of course, faster. Discussion. So in this work, we essentially focused on the architecture. And like natural language processing and computer vision, the transformer architecture is also successful to solve combinatorial problems, TSP, but you can imagine you can easily extend to other combinatorial problems. Further developments, so straightforward developments will be to improve, the sampling techniques, like a group beam search or Monte Carlo tree search. That would be a way to improve the results. We can also use intermediate rewards, like to opt. So far, in what we've done is only using a global reward, which is the length of the tool. But we can get, intermediate rewards to improve the learning. So we have promising results, but we need to moderate our optimism. So today, traditional solvers like Concord or LKH3, they outperform learning solvers in terms of performance and generalization. Neural networks are faster, but they are not as accurate as traditional solvers. So what's next? So something which is interesting is that we can learn longer because we can generate an infinite number of training data in combinatorial optimization. It's very different from natural language processing. Here we can generate as many training data as we want. So you see that the training curve, still go down. We can do better. But at the same time, we don't want to train forever. Natural questions are: can we improve the architecture beyond transformer? Can we have better learning paradigm beyond reinforcement learning? And of course, a very important question is how to get to very large number of cities, like 1 million cities, for example. And this is a limitation today with transformer because we have a quadratic complexity. So recent technique based on graph subsampling and merging look promising, to scale up. We can also consider harder TSP problems. So TSP is a kind of MNIST of combinatorial optimization, but you can imagine harder problems with more complex constraints where GRB and LKH3 could only provide weaker solutions or would take longer time to solve. We could also consider much harder combinatorial problems where traditional solvers like Jurobi can be used. So here you have linear complexity. You can also do quadratic complexity. Linear objective and quadratic objective with convex set. But with reinforcement learning, you would be able to do non-convex objective and non-linear constraints. That's something that you can do. Something also which is very attractive in the coming years is to combine traditional solvers with learning techniques. So if you take, for example, branch and bound technique in traditional solver, remember that sometimes you need to make a choice where if you are going to select this variable or not. So today, to make this selection, it's a human engineering heuristic, for example, strong branching, which has a very high quality solution, but it takes a lot of time. So recently, Lodi and Nair and their collaborators, they decided to mimic this branching rule. So during training, it takes a lot of time, but at inference, it's just very fast. So they were able to speed up traditional solvers like this. So this is the idea. If you have traditional solvers and if you need to make a human engineering selection, then now with learning techniques, you will be able probably to mimic or to improve this heuristic by reinforcement learning. Conclusion, combinatorial optimization is pushing the limit of deep learning. Traditional solvers still provide better solutions than learning techniques, but traditional solvers have been studying for quite some time, and the interest of applying deep learning has just started. So this topic will probably expand in the coming years, because in industry there are many problems relating to assignment, routing, planning, and scheduling. So that's really a strong motivation to develop these techniques. Novel software will be developed based on continuous discrete optimization and also learning techniques, such as eCall. Material for this talk are the archive paper, GitHub code, and also this article for general audience. The last slide I want to use is if you are interested in this topic of deep learning and combinatorial optimization, we organize a workshop at IPAM UCLA, and all videos are available on YouTube here. Thank you so much for your attention.
Thanks for the wonderful talk and insightful information, Xavier. So we have a few questions here on the Rocket chat window. So first of all, one question is whether this technology can easily be extended to vehicle routing problem.
Yeah, sure. So TSP is a particular, instance of a vehicle problem. So in some sense, TSP is I would say the most basic one. So if you're able to solve TSP, then you would be able to extend to diverse vehicle problems. So it just, I would say like the MNIST, problem for combinatorial optimization. If you're able to solve this problem, then you can extend to several other, problems of the same class. So here, I think it's a very flexible algorithm, and we can extend to different, constraints, different objectives, and different, of course, problems. So yes, the answer is yes.
Okay, great, thanks. Another question we have here is when the number of nodes increases, the training data for RL will also need to increase. Do we have some results about this relation?
Yeah, so we are using, transformer neural networks. So we know the complexity is quadratic with the number of nodes, the number of cities. So you have the quadratic complexity. This is, what come with transformers. So they are powerful architectures, but they are not linear, complexity architectures. So you need to pay more price, if you want to get higher accuracy. So this is problematic. If you want to scale to not, hundreds of cities, but you want to scale to thousands, millions of cities like, you have in industry. So you need, in some sense, to go back to linear complexity. Mm-hmm. So to do that, you you can have approximation of transformer. So at the core of transformer, you have the attention mechanism, which is a quadratic, complexity mechanism. So because transformers are very popular, people develop some approximation technique to get linear complexity. So that's something we can do as a future work to get this linear complexity. Another, I would say an alternative, and one paper already, explored this direction, is to subsample, the data set. So if you have, for example, if you train on let's say 100 cities, and then you have a TSP of the size of 1,000, what you can do is that you can subsample 100 cities of that, and you can do many of this subsampling of 100. And then you will find a way to, so you will solve the problem at 100, and then you will find a way to merge the results for 1,000 cities. So one paper has a very promising result in this direction. So in some sense, solving the problem at 100 can be quickly done. And then when you merge the result, this is something that can be done in linear time. So there are some, future directions to scale up this technique. So in some sense, if people get interesting in doing deep learning for combinatorial optimization, I'm pretty sure we will, find ways to speed up and scale up these techniques. It's just, I think, a question of interest. And again, industry has a tons of combinatorial problems. So many standard problems are well solved with standard algorithms, but when you start having complex, like non-common combinatorial problems, then probably this is where neural network will be quite useful to use.
Thanks for the answer. Now, I have maybe one. Okay, there's one more question popping up. Will transformers be able to handle the TSP with constraints, for example, like time constraints?
Yes, absolutely. So transformer is just a function. So you're just going to use a function to make an to answer, you want to minimize the length, for example. If you want to minimize the length with some constraints, additional constraints like, time constraints, what you will do is that you will simply add these constraints in the loss. So you have, the standard loss, which is the length of the tour, but you can add additional, losses where you have this time constraint. So this way you will constrain the policy to satisfy the length, but at the same time also to satisfy some time constraints. So as long as you can model these constraints as an objective, then you will be able to add this to your learning process, and you will learn a policy able to optimize this particular loss.
Thank you. Any more questions from the audience? Now, another question I have for you is that, we know TSP is one of the most classic combinatorial problems, and I'm wondering, is this technique you're introducing can apply equally well to other, proven NP-hard problems, or is it constrained to problem of certain structure? And why did you choose TSP to start with? Applying this technique.
Yeah, thank you for the question. So we started with TSP because TSP again is like as you said, this is the most fundamental problems in combinatorial optimization, starting with von Neumann, with all the great mathematicians and also great computer scientists working on this problem. So in some sense, it's kind of very risky to start working on TSP because there are so many already research done on this problem. So if you want to publish, I would say don't do TSP. You try to do something less popular than TSP. But still, if what we wanted to do is to get some insights. How can we solve this problem that has been solved for so many years? And if we can have competitive algorithms to do that, then we will have some insights and properties that we can use to solve other combinatorial problems. So that was really our motivation. It's very hard to compete with the standard algorithm like Concord, but what we can learn is very important to generalize to other combinatorial problems. So it's just the beginning. So other people. So there was this workshop we organized, at IPAM UCLA, and there are many other combinatorial problems. People try to use deep learning. So it's not something that is only successful on TSP. There are actually many other problems, max cut, for example. And there are many other computer problems where people already start, applying deep learning on graph, for example, to get, good solutions. And what you see, which actually is very interesting, is that most of the deep learning techniques used on these different combinatorial optimization problems are actually better than the standard algorithms. And the reason is standard algorithms are actually too weak to give you, a good solution. So this is my point. And where I think, is going to be potentially good for industry is that in industry, you have many hard combinatorial problems, not only TSP, but you have TSP plus a lot of constraints. If you have, Alibaba or Amazon warehouses, you want, to solve many TSP variant of TSP problems, to allocate your resources and retrieve your resources very quickly. So this is, it's not easy mathematically, to do some kind of Concord, algorithms to solve this problem. But with neural network, it's very easy. It's very flexible. As long as you can, as I said before, model your constraints, in an objective way, then you just, run your GPU for a week, 2 weeks, and you will get, very good performance for your algorithm. You will find, the system will find, a good algorithm to solve this problem. So yeah, that's very promising, I would say.
Thanks a lot. I think this is a really interesting direction. And yeah, as you said, TSP is really a very classic problem. I remember, when I was in PhD days, if I go to theory conference, there's always like a group of people who always just publish on TSP problem every year after year. So yeah, I really admire your courage to start on this line of work, especially combining the state of the art, the hottest machine learning algorithm with this very classic combinatorial problem. Thank you again. Thank you for the wonderful talk. Okay.
Thank you very much. Thank you, Professor Zhu. Thank you very much.
Okay, bye-bye.
Bye-bye.